So I'm interested in interaction between light and matter, and when I say light, I mean photons, and when I say matter, I'm restricted to atoms. In particular, this talk will be about cesium atoms. And, well, I can skip this. And as we have been listening in the last session, what we want to do is increase the probability of interaction between a photon and a field of light. Usually this interaction that we just learned from Luis, that is the atomic cross-section divided, is proportional to the atomic cross-section divided by the area, and we can think about the geometric aspect being like the wavelength squared divided by the area. Usually that probability is really small. And also, as we learned, there are ways around this problem. Usually you can focalize the light in order to reduce this mode area, and that really works. But there are some problems. For example, the light diverges really fast, and it's complicated to interact with a lot of atoms in this really small volume. The other one is cavity QED, both bulk or nano, where the probability of interaction is enhanced due to this bouncing of the photon inside the cavity. So this we just learned. And the approach that I'm interested in, that is Waveguide QED, that is a strong confinement, a strong transversal confinement of the light in a waveguide. And as we know, we have the Corzo effect and all these interesting effect that Luis just told us. And in particular, I'm going to restrict myself to the case of a nanofiber. So, an optical nanofiber. What is an optical nanofiber? It's a normal nanofiber whose diameter has been reduced to dimensions that are smaller than the wavelength of the light that is traveling to it. Okay? I just need the students to really put attention. The diameter of this nanofiber, in this case, we will assume to be 400 nanometers. That's the diameter. And I'm telling you that a light with a wavelength of 852 nanometers, because it's cesium atoms, is traveling to it. Just realize that the wavelength is larger than the diameter of this thing. In principle, seems really hard to believe, but believe me, it works, and it works really well. So we start from a normal fiber where the light is bouncing between the core and the cladding, and we start reducing this diameter. I will explain you how. And at some point, the light is traveling in the interface between vacuum and the silica. And if we are careful enough, we can make this nanofiber length of the orders of 1 centimeter or 5 centimeters. And also, in this region, the light is strongly localized, and there's a strong evanescent field that is traveling in this region. So the light is really focalized over a length of centimeters, something that cannot be realized in free space. Okay? And if we are really careful, we can have minimum losses through this system. My fibers were not that great compared to Luis Orozco's fibers, where the transmission was 99.999, and I don't remember how many nines. But yes, the transmission was
never enough.
Never enough, yes. So this is a great advantage. I can make the light interact really strong with any emitter that I can put here, that is going to be atoms, and I can bring the light and take the light out using commercial fibers. So that's one of the great advantages of this system. And all these strong comparative effects that Luis was talking about, they are all realized in a single pass. I don't need the mirrors or anything. Just by focalizing the light in this region, I can have a strong, the strong coupling in some sense. Okay? How do we realize these nanofibers in the experiment? Is basically you have a piece of plastic. What do you do when you have a piece of plastic? You burn it. Okay, but we do it in a really controlled way. We have a flame that is pure hydrogen plus oxygen. Why it has to be that way? Because when you do the combustion, whatever is your dirt is going to be water. That's all you get. You don't have any nasty things. And what we are doing is pulling or brushing the normal fiber, and at the same time we are pulling. Okay, so we do that, and one of the main things that you need to take into account in order to do these nanofibers is that you need to conserve volume. So I'm going to stretch this nanofiber, but then the length is going to increase. Okay, and everything is well controlled using the computer, and we can have any profile that we want, any diameter we want, if we assume this conservation of volume. I just want to tell the students that when I arrived, I didn't knew about anything about this, but it's really interesting because you learn about pulling a nanofiber, then you are thrown into a microscope, an electronic microscope, and you are telling, okay, measure this. So you learn about different things when you do this type of experiment. Okay. Well, one interesting thing that also Luis briefly commented about these nanofibers is that the polarization is not the normal polarization that we can have in free space, like in this pointer. And I like to make my students have a lot of homework. So for the students here, I just want you to think about this in terms of the Gauss law and try to explain how can you have a longitudinal component in the polarization that is traveling in the same way, in the same k vector as the wave. So the polarization is strange in the first case. So this is the transverse polarization in a quasi-linear polarization like the one showing here. But there's a strong component that is in quadrature to the transverse polarization, but is a longitudinal polarization. That is really strange. So usually when we learn about polarization, if the light is traveling this way, it can be linear or circular in this direction. But in this case, the light traveling inside the nanofiber has a polarization in this direction, but also in this, there's a strong component here. So then you can have a circular polarization that is not orthogonal to the direction of propagation. And this polarization is different if the light is going in this direction than in this direction, and it's different if the emitter is on top or in the bottom of my nanofiber. Another interesting thing is that the mode that I'm going to talk about is the hybrid H11 mode, where the distribution in this polarization configuration, the distribution of the intensity, you can see that is more intense in the top and in the bottom on the nanofiber. And I want you to remember this property because it's going to be important for what I'm going to explain later. So in this nanofiber, with this polarization, intensity is stronger in the top and in the bottom. Okay? But I told you that I want to do interaction between photons and atoms. So what is the thing I can do? Is I can have my nanofiber, have a signal traveling to it, and then put atoms around it. This is similar to what Pablo and Luis talk and the paper they have. I'm going to put a magnetic optical trap of scission atoms around the nanofiber, and I'm going to release them. These atoms are going to start, they are cold, but they are going to start falling through the region near the nanofiber, and then my signal will get absorbed due to the presence of these atoms near the nanofiber. And this is basically what we do. We have here the input power and the transmission, and we can see that it gets saturated really fast, which means that I really have this strong coupling between the light and the atoms. And using this system, I can have optical depths around 3 for one of the important transitions in the scission atom. But this was not enough for me. I don't want to have the atoms fall around the nanofiber. I want to trap the atoms. And this comes back to the talk of Karina yesterday, and one of the questions that Luis had, how to trap the atom. And I'm going to trap the atom using dipole traps. So Luis commented in that question that you can think about this as a dipole, the atom as a dipole. Let's assume that I'm centered in the transition that's 852, and I want to trap the atoms. So if I use a red-attuned beam, here is around 935 nanometers, is red detuned compared to this transition, then the atom will go to where I have the maximum intensity of that laser. If I have a blue detune, then the atom will be repulsed at the high intensity. So if I have more intensity, it will go towards that. If I have blue detune, it's gonna get ejected. Okay, so that's the trick. But this is a really particular trap, dipole trap, because I have, in principle, 4 beams. Why do I want 4 beams? First, let's just focus on the red detune one. The red detune one here is the same as this one. So what happens when you have 2 lasers at the same frequency? They are gonna interfere. So you are gonna have an optical lattice. So the atom of cesium will go to the maximum of this optical lattice. I wanna try to be there. What is the blue detune doing? The blue detune is trying to prevent the atom from sticking in the nanofiber. Okay? The blue detune is not the same. Is not at the same frequency here. Actually, they are from 2 different lasers. So they are not going to form an optical lattice. The only purpose of those 2 blue beams is to prevent the atoms from sticking in the nanofiber. And the red detune is actually going to trap the atoms at the distance that is half of this wavelength. Okay. So I'm gonna have potential traps that are 935 over 2, and that's the distance between these atoms. And as I asked you to remember, the intensity is maximum at the top and in the bottom. So these chains of atoms are going to be at the top and on the bottom of my nanofiber. Okay? One interesting thing also about this trap is that it doesn't like to trap more than 1 atom. If you try to put another atom, what is going to happen is going to release the 2 of them. So in this site, I only have maximum 1 atom per site. Okay? And by doing this, I can have optical density of more than 100. Remember that here I had like 3. And my lifetime I can hold the atom for around 25 milliseconds, rather than the microseconds that is when they are released from the optical nanofiber, of the magnetoptical trap. Okay? So this is my system. Now I have this nanofiber, I have the atoms trapped around the nanofiber, and the final thing is that everything is done inside the fiber. Okay? All the beams are traveling in the same nanofiber. That allows me to use really low power to do this dipole trap, that usually in free space is around tens of watts, hundreds of watts even, but here I'm only doing the trapping with a few milliwatts and a few microwatts, okay? And that's because I'm using the nanofiber to do the trapping and the interrogation, okay? This is the high optical depth and the lifetime. And with this system, we have realized optical memories, Bragg reflection, but I'm not going to talk about that. I'm going to talk about the atomic excitation. I think Pablo already talked about the excitation in this type of system. And in particular, I'm going to try to realize this process in order to have a quantum repeater. This is based in this seminal paper by really, really smart people, where one of the main ingredients is to have an atomic ensemble. And the key ingredient is to have a high optical depth. Okay? Why it is important the atomic ensemble is because you have really, really different copies of the same system. Imagine that you have a system of n atoms, all of them in the ground state, and you excite only one of them. But you don't know which atom was excited. So your system will be in this state where all the atoms are in the ground state except one, but you don't know which atom it is. Okay? So in order to accomplish this, this is the system that I will have. These are my trap atoms, and then I'm going to realize this DLCC protocol that is called. But how does this look? Imagine that you have all the atoms in this ground state, and then you shine a bright beam that is not on resonance, is to the red. And this bright beam is so weak that only one of the atoms is gonna be excited and will decay in this region. And when it decays, it's gonna emit a photon that we are gonna call field 1. So if I'm able to measure this photon, then I can tell that one of these atoms was excited to the other level. Okay? I'm not gonna know which atom was it, but for sure I'm gonna know that at least one of them passed. So I will have a system like this, where nothing happens, or there's a small probability of excitation where one of the atoms is here, and I have one photon and the state that I was talking about. One atom has been excited to the other level. Okay? And so if I measure this photon, I can herald this excitation. I know that that excitation happened. Okay? But how do I study this excitation? Is by an additional beam that I'm going to call the read beam. This read beam is going to bring this atom back, and when the atom decays to the ground state, it's going to emit another photon. Okay? So then all the correlation, all the information that I have between the photon and the ensemble is going to be transferred to a photon in field 1 and a photon in field 2. Okay? All I need from this read beam is to transfer this information. And then I will have non-classical correlations, if I do everything correct, between the field 1 photon, between this photon and this photon. Okay? So this protocol has been realized before. For sure I'm not the first one. It has been realized in free space, in different groups. It's one of the, is really needed for quantum repeaters, and also for quantum entanglement between different and far away atomic ensembles. But it's the first time that it's going to be realized near a waveguide, and it's the first time that it's been realized in this kind of atomic register, when you have all these atoms near to each other in an ordered manner. Okay? So how the experiment looked like. This is the experiment. Maybe for some students it seems really weird, but what I can tell you is here inside this vacuum chamber, that's where the nanofiber lives. All the lasers that you will see here are needed to cool the atoms. These 3 lasers are needed to trap the atoms, and all this filtering is all this optics is needed to filter the photons that I want to study. Okay? Here you can have a better look of the nanofiber. You can see that the camera is not really able to realize the nanofiber, but you can see that this is the region where the nanofiber region exists. And here's the experimental setup in a more clean way. So I have the vacuum chamber, my nanofiber and my trap atoms are here. This laser, this red laser is divided here, so it's going to realize the optical lattice inside here. The blue lasers that are at different frequencies are going to push the atoms far from the nanofiber, and then I need filtering. In my case, the filtering is a cascade, 2 cascade volume Bragg gratings, and then some polarization filtering and some cavity. And here's another part of the homework for the students. I told you that I'm doing everything in the nanofiber. I told you that I'm trapping the atoms in the nanofiber. So actually, inside the nanofiber, you can assume that there is like 10 milliwatts of this blue laser, let's say. 10 milliwatts. Then the question is, how many photons are in 10 milliwatts? And then, why this is important? Because I want to be able to see only one photon that is being created here. Well, 2 photons, one for field 1 and one for field 2. So when you go back to your school, try to do this calculation. How many photons are in 10 milliwatts? And then we need a lot of isolation. So here I have around 160 dB of isolation, and the transmission is around 40%. So it's not that bad transmission. We can see now the results. So the results are going to be between the two photons, the photon in field 1 and the photon in field 2. And the first thing to do is to do the cross correlation function between that. That's the parameter G12. That is just the joint probability, and then these are the individual probabilities. And you can see that if this P1, that is the probability of detecting the photon in field 1, start to increase, then this cross correlation is going to start to decay. Okay? But if you are really doing a low excitation probability, then this correlation starts to increase. And actually, the classic limit here is around 2. If you want to do some entanglement between the different ensembles, the limit is around 25. And here I'm above those thresholds, so I'm around 100 for G21. So this is the correlation between the photon in field 1 and the photon in field 2. They are correlated, okay? But that doesn't tell me much about the single excitation that I created in this arrange of atoms. So what do I need to calculate is the QC parameter, that you can understand this as the efficiency that I have in order to recover the second photon once I have detected the first photon. Okay? I wanted this to be super high, but I'm limited in this part to be around 25. And here you can see 3 different regions. Well, remember, I'm plotting the same factor, P1. So I have a lot of photons here, more than one. Here is the region of only one excitation, and here I have noise from my detectors. This is, so I have more photons, but you need to remember, these photons are not correlated because they are coming from different processes. The only important ones are the ones that come from the single excitation. And in this region is where I have this G12 that is higher than those thresholds that I wanted. What is happening here is because of the dark noise on my photodetectors, then I have bad counts that start to diminish my measurement. Okay? And the final measurement that we can do is how good is the second photon once I detect the first photon. This can be understood as the G2 measurement for a single photon source, but it is not really G2 because I'm heralding on the photon in field 1. So basically, if I have a photon in field 1, is the other photon really a single photon, or there are pairs of photons there? And in order to do this is why I have 2 detectors here and a fiber beam splitter. So once I have a click here, I want to see if I have 2 clicks here. Remember, if I have only one photon, I will never see 2 clicks at the same time. Okay? I will have a G2 of 0, and in this way it will be a parameter W of 0. So basically, I want to measure something that shouldn't happen that much. This parameter, this W parameter, shouldn't happen. So in order to take the measurement, also for the students, in order to have this point, I had to be running the experiment for 6 hours in order to have enough counts and enough data to have low noise. Okay, 6 hours just to have this point, because I'm trying to measure something that doesn't happen, that I have the 3 coincidence. Okay, and I was also able to extract the profile of the photon. That this has to do with the excited state of the scission atoms, but also to the fact that I have an atomic ensemble and it's not only a single atom. So you can see more of the results here in arXiv or in the paper. So I have a heralded single excitation, only one excitation. I generate correlated photons, and I was able to measure this W parameter to be really low compared to the classical limit of a coherent state. And also I am able to measure the the waveform of the photon. So what is next in this particular experiment is I want to shape this photon. Rather than being a Gaussian, I want to be a really long Gaussian, maybe an exponential decay. And I want to generate a deterministic source of single photons. So I need to do this experiment and in addition a quantum memory in order to be storing these photons. Maybe I can build a switch or a gate that works a really low photon because of the high interaction between the light and the atoms, and maybe do some quantum entanglement between different atomic ensembles. Like I can take this ensemble that is near an fiber and then entangle this ensemble to an ensemble in a simple mode, okay, and do this entanglement at really far distances because my photon will be traveling in a optical fiber, okay? Not that yet. So now we are in the lab. So we are building our lab here in Querétaro. It's under construction, but it's getting there. So we have some installation for fibers or PNC cables or optical tables have arrived. So it was really challenging to put the optical tables in the building, but they are there now. Optical tables, and we need students, okay? That's the thing that we are missing most, the students. So please contact me, and in order to encourage you, this is how the lab is gonna look like. You will have a lot of lasers, lenses, mirrors to play, beam splitters. Everything looks really cool using lasers. Seems really complicated, but in some sense, even it looks like a spatial shuttle. You can work here for several hours per day, and you will learn a lot. Of course, you will learn physics, you will learn optics, but also electronics, programmation, even plumbing, control, data analysis that is really important if you are going to look for jobs in the future. So everything here you will learn in this type of experiments. And I should have quotes here, but I don't know if this is from you, Bill, but it has been in all my talks for a long time, so I forgot who said it. But one of the really nice things about colatoms and photons is that you can have a system where you can really play with quantum mechanics, okay? So usually you go to quantum mechanics class and you start doing some homework, some problems, but in the lab it's a really good way to play with quantum mechanics. So I want to encourage some students to join the group. Thank you.
Okay, thank you, Neil. We have time for maybe 2 questions. Bill, please.
So you showed that the atoms were trapped for something like 25 milliseconds, extending their lifetime by a big factor. What limits it to 25 milliseconds? What's happening that makes them leave then?
That's something that we haven't understood yet. In principle, because this trap that we're using, it was based on a trap that Kimball did at Caltech, and they have a lifetime of 300. They report that. And we're believing that our vacuum system is not that great. Because one of the key points here is that you need to put enough air inside vacuum, but you need to escape vacuum. And in order to escape vacuum, you need to actually just crush a piece of plastic that will allow you to create the vacuum. So you have the fiber entering the vacuum, and then you crush a plastic here. So we're assuming that our system is not that great compared to that. But in principle, should be 200 of.
One more question? Okay.
Yeah, that was a really nice talk, thank you. Is there an issue if the atoms get too close to the fiber? Or what does that interaction lead to?
The problem is once they are really close, like van der Waals interactions start to play a role, and then you cannot remove them from the fiber. You can put light and it's going to stay, the atom will stay. fiber forever, basically. So usually what we do every day is we work, we make the experiment, and the only laser that we never turn off is the blue laser. The blue laser is there all the time to avoid these atoms to stick in there.
But even if they don't stick, is there some, like...
Oh, okay, if they don't stick, then it's good, because actually I want to be as close as well, closer than I am right now, because the interaction will be stronger. So in order to do this nanofiber more interesting, yes, I want the atoms to be closer than that. One thing that I forgot to mention is that this dipole trap is also really special because it is trying to minimize the scalar shift and the vectorial shift that we have in dipole trapping. So, and we want to trap the ground state and the excited state. So that's why we cannot play that much with the power, with the intensity, with the power and the wavelength of these lasers in order to change this.
Okay, so it's time to move on. Let's thank